In this video, we'll discuss ideal gases. But before we discuss ideal gases, let's do a little bit of review. So, we have some values here. Which set of values represent STP? Now, hopefully you looked in your reference table. You should be looking at table A. If you looked at table A, you would find that STP, remember, stands for standard temperature and pressure. So the values for standard pressure are given first. They're either 1 atm or 101.3 kPa. Sorry about that. Or if we're looking at temperature, it's either 273 Kelvin or 0 degrees Celsius. So now that we know what those values are, we can look at our answer choices and see that the correct answer for this case would be C. Remember, you don't have to memorize these values, although it helps to know them. But remember, they are definitely on the front page of your reference table in table A. So in our discussions about gases, we've talked about gas pressure and how gas pressure is pretty much a measurement of the collisions between the particles and not themselves, but as we can see here, the surface of the container that they're being held in. So in this situation, we have low volume, and here we have high volume, and I'll just put HV for short. So remember, this is going to actually control how much space they have, and then that amount of space they have is going to actually tell us which situation gives us more collisions. So when they're squished together, less room, you're going to have higher pressure because you have more of a chance of getting a collision in this situation, versus when there's more space in between particles, the likelihood of collision is lower because they have more space. Then we can also look at temperature. At a lower temperature, particles move slower, and then you'll see where you can even have the gas starting to not behave ideal-like or we want gases or expect gases to behave, and those particles start getting closer together and slowing down. Versus at a high temperature, that's when you're guaranteed you're going to have gases flowing as fast as possible. When they're at when they're at a high temperature and they're moving really fast, then you're definitely guaranteed to have ideal gas behavior. So we're talking about ideal gas behavior because we've been studying gases for a while, and we know that they don't always behave ideally. So in situations when we're talking about real gases, when we change the conditions, and when we're talking about conditions, we're talking about either the pressure, the volume, or the temperature. When you change one of those three conditions, you can actually force gases to change into liquids and even solids. And that's because you start having attractions between those particles, and that's either going to happen if you slow them down or if you push them close enough together for them to start to form those attractions. This is not ideal, right? Gas particles are supposed to be chaos, right? Moving around freely with no attractions. But when we change those conditions, then they behave more real or less ideal. So the easiest way to remember ideal gas conditions, because remember, there's no such thing as an ideal gas. There are just conditions that guarantee a gas will behave ideally, aka a gas will definitely behave in chaos like we expect them to. So here's a mnemonic device called PLIGHT. It stands for pressure low, ideal gas, high temperature. So those are the two situations or conditions that are going to guarantee you an ideal gas, or gas is going to behave ideally. Because remember, at a high temperature, those particles are moving as fast as possible, and at a low pressure. Now notice we don't mention volume here, but remember, pressure and volume are related. So, but as long as you have a high volume, right, you give them a lot of space, that's going to cause low pressure, and that means, like we see in this visual, the gas particles can be as free and move around in a straight line fashion as much as they want. Versus when those conditions are not ideal, that's when you start getting clumps, right? This is not how gas particles prefer to behave, but understand at a lower temperature and a higher pressure, this is what we mean when we say when the gas starts behaving like a real gas because you've changed the conditions. But for this lesson, we need to understand the ideal conditions or a situation the gas wants to be under. And as a reminder, that is with a low pressure. So that's what the PL stands for, pressure low, or a high temperature. So let's do this check for understanding question. Real gases behave like ideal gases until they encounter low temperatures and high pressures. What happens to gases at low temperatures and high pressures? Hopefully you said something as far as attractive forces take over and gases can form liquids and solids. You also could have said something like the particles move slower and become closer together. All of those answers will be considered correct. Now, the last thing we need to know about gases is Avogadro's hypothesis. So Avogadro was a scientist who dedicated his life to studying matter and especially gases. So during his experiments, he noticed that gases under the same conditions, and we've been talking about these conditions for this entire lesson, and that means the same pressure, volume, and temperature. He noticed when they're under the same pressure, volume, and temperature, they have the same amount of particles. Now, particles can stand for either atoms or molecules. It all depends on that actual substance. For example, helium here is just a singular atom. That's how this element here is represented, versus nitrogen is considered a diatomic, which just means a molecule made of two of the same atoms. This is also an element, but in this case it would be considered a molecule, remember, because you have two of the same atoms bonded together. Versus our last example here is methane, and methane is also considered a molecule because it's a group of atoms. And this one I know is actually a compound because they're different atoms in this situation. So Avogadro was actually able to compare elements as far as if they were atoms, molecules, and compound molecules. He noticed that as long as they were under the same conditions, so here they're all under 22.4 liters at 1 atm for the pressure and at 0 degrees Celsius. As long as the P, V, and T are the same, they all have the same number of particles. So for helium, that particle would be atom. But for nitrogen and methane, both of those particles will be molecules, and I'll just put MOL for short, molecules, because they are groups of atoms. So that's a big number, 6 sextillion. But you don't have to memorize that number. You just have to understand that no matter what these numbers are, as long as the pressure, volume, and temperature are the same, you're going to have this number is going to be the same for every sample of gas because they're under the same conditions. Now note their masses are different, and that's because they're different. Helium is just one atom, nitrogen is a molecule of two of the same atoms, and methane is a compound made out of a combination of 4 atoms, right? So of course, different elements, different sizes, your masses are going to be different. So Avogadro's hypothesis is not about mass, it's all about number of molecules or atoms. So if we're looking at this, if this was representing a picture, we literally just be saying that I have 6 sextillion of these atoms floating around, 6 sextillion of these molecules floating around, and 6 sextillion of these molecules floating around, as long as they're under the same, in this case, 22.4 liters, 1 atm, and 0 degrees Celsius. So in summary, just don't get stuck on the numbers. Just read these problems very carefully, and I'm definitely going to end with a practice problem for you. But for Avogadro's hypothesis, as long as they're under the same pressure, volume, or temperature, you have the same number of molecules, no matter what the formula is. So don't let the formula confuse you. And the easiest way to remember pressure, volume, is temperature and temperature is, remember, we've been using the combined gas law. That has the three conditions that we can change, and those are also the three conditions that have to be the same with Avogadro's hypothesis. So it might be something to write on your reference table as a reminder. So as long as here we have helium, oxygen gas, water gas, and ammonia, different formulas, but as long as they're under the same pressure, volume, and temperature, you have the same number of representative particles in these balloons. So let's go ahead and look at a practice problem. Which rigid cylinder contains the same number of gas molecules at STP as a 2-liter rigid cylinder containing hydrogen gas at STP? So if you look here, you're given different volumes and you're also given different gases. So they're telling you that it's at STP. Remember, STP stands for standard temperature and pressure. So all of these gases are under the same temperature and they're also under the same pressure. According to Avogadro's hypothesis, though, they have to be under the same conditions, and those conditions are pressure, volume, and temperature. So since we only have temperature and pressure here, then your other hint is that they've given you the volumes. So to answer this question, you're looking at the option that has the same volume as the hydrogen gas. Since the hydrogen gas has 2 liters, the answer for this question, according to Avogadro's hypothesis, would be B. And it would be B because B also has 2 liters. So it has nothing to do with the formula. So there's no trick as far as actually, it's simple. You don't have to look at coefficients. All you need to do is find the option that matches the conditions that are given in the original problem. So other than that, all you have to do is remember Avogadro's hypothesis and then remember plight. Ideal gas, or a gas is going to behave ideally when it's under a low pressure or if it's under a high temperature. And that's all for today's lesson.